Hi, everybody. So, at least unfortunately for me, this is the last technical lecture we're going to have for the VLSI design class this semester. There's a lot more stuff to cover, of course, so I wish we'd had a chance to look at a bunch of different items. And I was pretty conflicted about what to cover now. I think we've covered a bunch of the core things. So, I had a choice between memories and, data pads. But I picked, one of my favorite topics, I/O circuits. So these are basically the interfaces to the chip and how you design them. Part of the reason, like I said, is that I like the topic myself. There's a lot of fun stuff, and there's a lot of analog-y kind of things. It's always a challenge to design I/O. And there's usually a lot of problems with I/O, which makes it, fun, I guess, to try to debug. And in addition to that, I think it's one of the areas that if you work with chips, FPGAs, whatever at all, even if you don't design the chip itself or the FPGA itself, you still end up seeing the external interfaces to the chip. So that's why I think you'll probably see things to do with I/O, even if you're not designing them. So let's talk about what this I/O is. It's basically inputs and outputs, and they have different functions. One of them is just obviously to communicate between chip and the external world. So on inputs, let's put it this way. Let me see if I can. Nope, half the time this thing works, the other half it doesn't. Well, anyway, so inputs, you might have a I²C. So these are serial slow inputs. You're setting the register settings for the chip. So I²C, SPI, serial pair interface. These are pretty popular, and these are 1 to 5 megahertz. You're basically doing setting up to the chip, etc. And then on the outputs or inputs, then there's the data itself, and then you might have sort of serial outputs or inputs. These might be anywhere between, I don't know, like a gigabit per second to 50 some odd, let's say 56 gigabit interfaces to the chip. That's pretty fast. You might have memory interfaces like DDR interfaces. Where mostly people are at DDR3 or DDR4 now. So these are the type, PCI, I don't know. There's a lot of different interfaces from low speed to high speed, but basically are communicating with the rest of the world. You are on chip, you're designing your on chip capacitances, like I mentioned early on, things you see on chip are on the order of femtofarads to picofarads. Maybe you'll see something at a nanofarad, like a decoupling capacitance, but it's rare. But definitely off chip, your capacitive loads are going to be much higher. Like when you're driving the pins of your package, you're driving the routes on your printed circuit board, you're driving the input of another part, you might be driving a coax cable. So anyway, the loads could be tens to hundreds of picofarads, maybe like nanofarads. Okay, so those have large. So you need something big to drive those. You're not going to be driving these kind of outputs with small buffers. Okay, so let's see. The next one is different voltage levels. It's, there's some typical voltage levels in a CMOS environment that we're used to. You'll see 1.2 volts. That's usually the core that powers up the insides of the chip at, say, 0.13 micron and below. They're all kind of operating at 1.2 volts. But outputs, you'll see a lot of 1.8 volts. You'll see 3.3 volts. By the time because it's sort of like a standard, you want to communicate to other chips. And a lot of the communication isn't at 1.2 volts. So you need some way to transfer or interface from this internal supply to these kind of external supplies, depending on what your requirements are. You'll see also 2.5 volts is another popular level. So basically different voltage levels. Bandwidth, it just goes through with like driving fast outputs. You see how, we're talking about really high speed, gigabit per second, multi-gigabit per second. So I need high speeds. But you need those high speeds without making a lot of noise. So if you guys recall, when we were talking about the package, we were talking about there's a lot of, potentially a lot of inductance because the wire bonds and so on. So if you have a very large buffer on chip that's driving a large load off chip, the current here, you're providing current to this very, very large capacitive load, which is outside the chip, like we talked about. And so, as you remember, you're pulling in a lot of current, a big delta I, as you are charging this guy up. And that will tend to put a lot of noise on these supplies because the change in voltage on the supplies is L, which is the inductance, and these tend to be high because they're wire bonds and so on, times the rate of change of current with respect to time. So we don't want extremely fast edges will make this DI/dt very large. So you basically want to have only as fast an edge as you need to reach your frequency. So you need to control these slew rates, is so-called. Slewing is when an analog circuit goes from point A to point B without really settling. So I won't get into the details of slewing versus settling, but if it's slewing, you can just think of it as a rise time. Then there are environmental issues out there, like electrostatic discharge. We'll talk about that a little bit. We're all familiar with it. It's sort of what you pick up walking across a carpet, but as I'm sure you guys know, it could be pretty destructive to microelectronics. You could build up, tens of thousands of volts, certainly thousands of volts. Very little current, mind you, but thousands of volts. And, if you zap your circuit without adequate protection, you can destroy it. And finally, there's the issue of cost. So, like serial interfaces, that's why they're very popular. Because the fewer number of pins you have, a lot of times the number of pins determine your package cost, and also, determine your package area, etc. So it's nice to have very few pins. So those are some of the characteristics of input-output structures. Okay, so there's different types of so the pad is not just, so what the I/O input-output looks like, let's say it looks like a buffer driving a large piece of metal, and you wire bond to that piece of metal. I'm really simplifying the drawing here because this piece of metal has, it's got a stack of layers underneath it, etc., to make sure you don't cause any problems, any mechanical problems. But the idea is that this might be landing. So this might be a landing pad, might be 75 to 100 micron per side piece of metal. Officially, that's sort of, or I shouldn't say officially, strictly speaking, that's called the pad. But, people like me call this whole structure a pad. So that's what this pad types mean. So you have, I drew an output pad there. There is you can have input pads. So this is, taking signals in to the chip. This is going out of the chip. You need to provide a pad for the ground. You need to provide pads for the supply. And you might have an analog bias, etc. So there's different types of pads. Each one of them has their own design methodology, let's say, and issues. So an output pad, a regular output pad, like I mentioned, has to drive a large load. Okay, you don't want to make the rise fall times too fast because of the LDIDT, because of LDIDT noise. And like we learned in the logical effort case, you'll probably want to drive, if you got a small, inside the chip, you've got small, say, devices and inverters. Let's say even if it's big, it might be like an 8x type of inverter. And, when you want to drive an off-chip load, that's, something like 50 picofarads, this end guy is going to be a pretty big device. It might be, it wouldn't surprise me to see stuff that the width in aggregate for the NMOS might be 500 microns. It might be something like that. Anyway, very large devices. So what you need is a chain of inverters, like we saw in the logical effort, to basically get the fastest overall delay to do that. So these devices, this chain of devices, to help you go from an internal, sort of a typical internal device to something that's big enough to drive an outside thing, is also part of the pad. So, and then the other part is protecting against, when you're interfaced to the outside world, it's like a very noisy environment. It's noisy from the point of electrical noise. It's sort of noisy in the way of mechanical stuff going wrong, if I can call that noise. But there's a lot of stuff that can go wrong there. So basically what you want to do is isolate these structures with lots of guard rings. So for example, let's say I have a N plus, let's say I've got a transistor, NMOS transistor, that's driving an output. Let's say that's the one of the half of the inverter driving my pad. You basically want to surround the entire area around this thing. So like something like this, with a ring of, you'd probably do a ring of P plus, an inside ring, and then you might even do an outside ring. In fact, you probably would do an outside ring of NWL with N plus going all the way around. In fact, I think this is an NWL ring here, going all the way around. And then you might have an inside ring that is the P plus. So it turns out, you think, well, what good does this do you? You could go through the substrate and, get noise out to other places. But it turns out that they do a sort of a shallow P plus doping everywhere on the surface where you don't define anything as a designer. They just do that P plus implant. And so that's a good way for noise to get around the chip. So by having these kind of breaks in that P plus layer really helps you out. And also if you're in an epi process, like we talk about, the epi thickness might be 5 microns or something. So the guard rings do help you. So, and then, there's this phenomenon, I don't think we talked about it, called latch up, which, comes from this, I won't really get into it, but it's a phenomenon that comes from having NMOS and PMOS transistors on the same chip. Because you have N plus P, N plus for the NMOS, and you have the N well, sort of the P substrate, N well, P plus for the PMOS, if some bad voltages happen, which normally don't happen inside the chip, let's say if you have a low going glitch below the ground level, which could happen if you're looking at the outside the chip, that structure that I just talked about is going to end up looking like two back-to-back bipolar transistors. Again, it's called latch up. So two back-to-back bipolar transistors, and then they're going to they'll give each other positive feedback, and that your chip will go into a condition called latch up, and it might be destructive to the chip if you can pull enough current, or it might just sort of freeze your chip. So the latch up is like a big issue or a big worry on these outputs. I have personally never actually in all my years, thank God, had a chip that had this problem, but it's just something you have nightmares about because it would be really a bad situation. Let's see. So guard rings and N plus guard rings and N wells. Okay, so we covered. That was the output pads. Input pads are a little bit different. So these are, you'd have a piece of metal and the input. So one of the things you need to do is maybe do a level conversion. Maybe you have a 1.8 volt swing here, and you need a 1.2 volt inside, or maybe you've got similar 1.8 volts, and you've got some 3.3 volt levels. So you do need to do a level conversion. I think we talked about level conversions a little bit a few lectures ago, but if you have a high to low level conversion, it's relatively easy. So you just use a regular buffer, and when you're going from a high supply, so let's say if you're going from a 3.3 volt to a 1.2 volt, you can just supply this 1.2 volt off of the 1.2 volt supply. You'll overdrive this input, but it'll still work. It'll do the full swing, and the NMOS and PMOS and those guys are going to do their thing. The only thing you need to worry about here is don't use, if you're going 3.3 volt, 1.2 volt devices have a lower breakdown voltage. That means their oxide gates could break down if you put in 3.3 volts into them. So you might have to use thick oxide. These kind of processes that have a mix of high and low supplies usually have a mix of thick gate oxides and thin gate oxides. But anyway, that's the only thing you need to worry about. Otherwise, you can just use a regular buffer. Now, if you want to go from a low voltage, so let's say you want to go from 1.2 volt to a 3.3 volt buffer, you've got a bigger problem, because what happens is this point here is only going to swing 1.2 volts. And, so the gate of the PMOS is only going to go up to 1.2 volts when it gets a high value, and this PMOS will not turn off. it'll still have a large gate source voltage across it. So it'll have both the PMOS and the NMOS on. So basically, this is the most popular level shifter. Basically, you have sort of a differential pair, pretty much. These guys, I don't know if you guys are familiar with differential pairs. And then a cross-coupled PMOS pair that's hooked up to this high supply. And they'll basically, by getting a small swing here, they'll basically, the PMOS FETs will flip and give you the full low to high swing here. And then, the other thing, the input pads you'll see a lot on is Schmidt triggers, and I don't know if you've seen those guys or not, but basically the idea is to have hysteresis in your transfer curve. So let's say your if you're going from high to low will have a different threshold or different switching point than low to high. And so this gives you some protection against noise, but that, once you've switched to a particular high or low level, then you'll have inertia to stay there. And they do that by, this is one particular approach, which you puts a weak PMOS and a weak NMOS here, and do what you said you really don't want to do, which is try to get the PMOS to pass a ground. But you're not really trying to pass a logic value. You're trying to just make it harder for this point to switch. And notice if you have a low here, this PMOS is on, and it's going to try to keep this point ground or close to the ground or to a low value, and it's kind of fight with you a little bit, trying to get to switch that, but it's not going to fight with you too much. It's just going to push the threshold, the switching threshold of the buffer in the direction you'd like to give you some hysteresis. And then finally, you'd like to have some level of protection against electrostatic discharge. You also need protection against electrostatic discharge in the output buffers, but it's not as bad a situation, because look at it in an output buffer. I'm just going to draw a sort of a simple inverter driving an output. If you have and we'll talk about what electrostatic discharge looks like. I can talk about it now, but imagine if you had a capacitor or something like that that's charged up to, I don't know, thousands of volts, let's say 2,000 volts. It can go up to that value because you're just dumping charge on this capacitor, and there's no place for that charge to go. So just, as you're just walking across the carpet or so on, you'll just build up charge on this. Once it discharges into something, there's not a huge amount of current, but it'll take some while for this voltage to go to discharge. And it's all about how long a period. If you can sort of bring that voltage down very quickly, then you can smother that high voltage before it does a lot of damage. And the good thing about output structures that gives them a little bit more protection than input structure is you have these sources and these two drains, on which look like, and if I look at those two drains for the NMOS, it looks like an N plus, and for the PMOS, it looks like a P plus hanging off of there. And what it'll do is if you're over or under your supply, there'll be like diodes clamping. So if you have a very negative going thing on N plus, this thing will forward bias and suck down the current into the substrate, and vice versa. If you got a very high going thing, it'll basically, this would be in an N well with this guy connected to say 1.2 volts, and this P plus will sort of turn on. The N 1.2 volts will be lower than the P plus is 2,000 volts, and the current will go into the well and get discharged into the other supply. So upshot is you get some level of protection because you have essentially these diodes. And these diodes will look like pretty giant devices, right? Because we're going to have pretty big devices driving the outputs. So it'll be a giant device with that drain. Those drain diodes will look like really big diodes. They'll be able to smother that current. You still need to take some other protections, but anyway, they're less susceptible to issues. In the inputs, though, the input pad, like I'm drawing here, unless you do something, all you see is a gate capacitance. You just see a capacitive load. By itself, there's nothing. If you dump like 2,000 volts there, it'll just kind of like sit there. It'll do charge sharing. So it might go down a little bit depending on what the capacitance that's creating the electrostatic discharge, what the value of that is versus the value of your gate. But you'll blow that sucker up. So you need to find some other protection against electrostatic discharge, specifically on the input devices. And we'll talk about that. Well, I guess we talked about it immediately. So the electrostatic discharge is something that builds up. There's human body. So just let's say people touching that, a chip, walking around the carpet. They don't have ESD protection on them, or smocks. There's different ways of to get rid of electrostatic potential. But let's say you don't have it and you zap the device by touching it. Then there's machines that do automatic machines that pick and place these devices to do high volume printed circuit board manufacturing. They can pick up electrostatic discharge. So basically the idea is you end up having a capacitor. Let's say it's a person. That's not a person's finger. That's not necessarily grounded, and this can get to pretty high voltages. Like I mentioned, it can be 2 kilovolts. It can be 10 kilovolts. It can get to pretty large values. There's just kind of no limit really until it arcs and discharges. And so you're connecting that up to a input pad of your chip when you touch it, and that can zap you. And so what you want to happen is you want to basically bring this thing down to a low level that the chip can stand before you damage the gate of it. So the idea is you'll get, so let's say I'm going to draw this. In fact, it'll look like sort of like something like this. So you have a diode clamps. So let's say this guy's at, you touch this guy with a sort of something, let's let me draw a capacitor with, say 2,000 volts. Okay. So right as you touch this thing, so time, and let's say this is the input, let's call that node X. So if I was going to draw node X, what happens is you put a resistor in series with your input pad, and that resistor prevents, makes an RC type of signal going into the input. So it's going to slow X going up to 2,000 volts. So it's going to be buying you some time. Okay, let's say this is 2,000 volts. And let's say this is 1.2 volts. Okay, so I'm drawing this in a break in the circuit. Okay, so it's going to be buying you some time. And then what happens is, as soon as this, let's say this clamp, it goes to 1.2 volts, this diode goes to your 1.2 volt supply. As soon as this node X goes to 1.2 volts plus a diode drop above it, this diode turns on and basically discharges this additional charge. So it kind of clamps that node to 1.2 volts plus a diode drop. That's when it latches, that's when it fires off. So that's the basic idea behind it. The idea is you have, you limit the actual current to a value with a resistor, and resistors aren't going to blow up. It's really mostly gate, transistor gate capacitance and stuff that are at risk. And so you want to limit the current that you have to get rid of, and you also want to slow it, the rise time of it off, so that basically gives your clamping circuits time to discharge that electrostatic voltage. Okay, so this is sort of a very basic. Things get much more sophisticated than that, but that's a pretty basic thing. You'd actually see these see these structures, and they're pretty. I think they're pretty effective. And one of the things you do is, whenever you design a chip, is you actually characterize it for electrostatic discharge. And you do that at different labs, and the way the structure works is you charge up 100. This is for what's called the human body model. There's also a charge device model and a machine model that simulate the electrostatic discharge in non-human, like I said, on a pick and place machine or something like that. But the human body model, it's basically you're taking your device to the lab and it's pretending like it's trying to simulate what would happen if it's a human that's touching this thing with the ESD discharge. And the way that test works is you charge up a 100 picofarad. These are all standards that, when you build a device, the customer says, I want this thing to be good to a 2000 volt. That's pretty typical human body model. That's like specified for your pads. So what you do is you go there, they put this thing, they charge up this 100 puff cap to 2000 volts, and then they put your device, they go through every pin to every other pin and do this. So for each one, they charge up the capacitor to 2000 volts, and connecting up two of the pins in your device. Then they'll connect it up through a 1500 ohm resistor to your device, and then afterwards, after they do all that, they go through and basically do IV curves on your inputs to make sure that nothing changed. So that's sort of ESD protection and ESD characterization, and very, very important. So this ESD is, again, a very scary issue. We've had structures that fail ESD, and when ESD fails, it's really, really bad news, because you can't fix it with just a couple of mask layers. You really typically have to go change all your mask layers and try to fix it. Okay, so bidirectional circuits, you can have pads that are both inputs and outputs. So so this would be the input side. You have buffer, you have your ESD protection going to these gates, and then you have the output driver. And the only trick is, the input's obviously not going to interfere, because the input's just going to be, it's not fighting with this point. But the output would normally fight with this point, so it could fight with your input. So the only trick is to have tri-state output drivers, to be able to turn off both the P and the N at the same time. And so when you're receiving, you turn off both of these guys. Remember, in a regular CMOS inverter, one of either the PMOS or the NMOS is always on. But in a tri-state driver, you can turn both of them off with this enable and either allow it to receive only or to drive only. Okay, analog pads, we really haven't talked about a lot about analog signals, but it's not necessary that you'd go to a buffer. You might be going to a current mirror or some kind of a analog structure. So they're sort of a beast of their own. I'm going to leave that alone as far as this class is concerned. So next we're going to just see a couple of examples of really old pads. But it's hard to show examples of pads because there's a lot of IP concerns around them, etc. So I think that's why we're looking at an older pad. So it gives you an idea about the pad size. This is like 200 microns by 200 microns total size, and this is the actual pad. It's 75 by 100 microns. This is where the wire bond would come and land on. And then let's take a look at, this is a bidirectional input. Let's take a look at some of these things. You've got some voltage clamps here. Okay, for ESD protection of your inputs. You have some resistors in series. You have a bunch of big sized transistors here for your outputs. So these need to be nice and big and beefy to drive the big output capacitance. You have your ground ring, you have actually ground, you have supply. So the idea, by the way, on the pads is there's going to be another pad here in your layout. So you want to set up the structure so that you'll get, when you butt these things up against each other, you'll get, you don't have to route the power and grounds to them. So you want to have all the grounds touching each other, all the powers touching each other, or all the rings touching each other. And so you don't need to do any wiring after you just butt the pads or the pads together. Okay. Here is UOFU. It's basically, I think, some university, but again, it's just sort of a smaller process. Just another example. Again, you get a feel for the type of size for the actual. This is called a landing pad. And it's, what's landing there is your wire bond. And, sort of the different sizes here. This is slightly smaller, but similar ideas. You'll see guard rings. You'll see big transistors to drive outputs. Those are the P MOSFETs there, the N MOSFETs here. They've sort of separated the N from the P MOSFETs here. This is to reduce latch up potential. Here's your input buffer. And again, you've hooked this up or laid this out so it could, your next pad could be sitting here and its VDD is going to be touching the VDD of this pad, its ground, its VDD, its ground, so that you don't have to worry about wiring these things up. Okay. All right, so those are the different flavors of pads. And now let's talk about some of the more interesting things. I mean, these were actually quite interesting, but another challenge is what happens when you try to go, have your outputs go fast. Earlier I mentioned, it's easy to be at, like, I don't know, I see a lot of stuff at 3, 6, 10 gigabit per second. I see a lot of those kind of outputs. And then, like I mentioned, you can go up to 56. You can get pretty fast on your outputs. So the question is, what are the challenges you get there? So, when you're driving something slowly, it looks like an RC. You can use an RC model. So it looks like the whole line is going up and down together. Maybe you've got a sort of a pi model. We talked about that to approximate sort of a longer line and the fact that not the whole line is going up and down together. But at some point, especially when you have lines that are, have more inductance, etc., like you would in an off-chip pad, your line is going to look like a transmission line. Okay, and what is a transmission line? Well, so all electrical signals go from point A to point B in the same way, as far as a classical physics type of model. Everything is an electromagnetic wave, goes from point A to point B. But sometimes the distances between A and B are short enough that you don't really, and the time frame that you're talking about is long enough that it just looks like you can model it as resistors, capacitors, these kind of things are all models of actual, how should I put it? These are circuit approximations like a resistor, a capacitor, etc., of electromagnetic phenomenon. Okay, so this is low speed and physically small model or approximation. Let's say it looks like an RC circuit. And the next thing is like a transmission line. And what happens, a transmission line, or it looks like a fiber optic cable or an electrical transmission line, you launch something into a transmission line, and sometime later it shows up here. So you'll launch in time in, and sometime later when this electromagnetic wave, basically because of the flight time of this rising edge, it gets to the other side. So when things get long enough and fast enough, longer and faster, you have your next level of abstraction, which is a transmission line. And then finally you still have to use, once you get past that point, you can't use that approximation anymore. You got to use your Maxwell's equations. But anyhow, so you can't, when you get outside the chip, you start talking about 4 or 5 centimeter length of lines, and you're talking about 10, 20 gigabit per second. You no longer can use this RC kind of approximation. You got to use a transmission line. Okay, and they have transmission lines. I don't know if you've seen transmission lines in any of your classes or not, but they have a couple of things. One is that they are, there's a flight time or a velocity for that E&M electromagnetic wave to fly through. And then they have something called the characteristic impedance that talks about how the voltage and the current, the relationship as the signal goes through that transmission line. So I think the first thing, the question is, when do we use this transmission line approximation compared to an RC line? And it really depends on a combination of the distance, so the length of the line, the speed of light in the medium, and the edge rate, like how fast the device is compared to the speed of line and the length. Okay, and the reason for that is if you're short, we're talking about a short distance between A and B. So let's say speed of light in a medium. So speed of light in a vacuum is, one rule of thumb is 1 nanosecond per foot. I don't know why I remember it in terms of feet, but that's 12 inches, I don't know, like 25 centimeters or whatever it is per nanosecond transmission. In things with higher dielectric constant, in say higher dielectric constant mediums like a printed circuit board, like a PCB, which is is made of some dielectric, FR4 is typical, that tends to slow down maybe to 2 to 4 nanoseconds per foot. I forget the exact number, but that's the speed of light. So if these things are, apart by 100 microns, and the light's traveling at 2 nanoseconds per foot, the amount of the travel time from here to here is going to be really, really short. So you can you basically look at this whole thing as an RC, like A and B are really moving together. If the distance between A and B is like 12 inches, like a foot, or 20 inches, then you just basically need to worry about transmission line effects, assuming that the edge rate, like even if you were far away from each other and you have a very slow going edge, okay, you can still, because these things are sort of incrementally traveling through this transmission line, you can still pretend like it's one chunk of metal that's going up and down together. So those are the sort of the considerations, and depending on the distance you're traveling, the speed of light in that medium, and the edge rates, you either have to use a transmission line model or not. Okay, so here's an example. So we have a 10 centimeter trace, and the question is, when do we need to treat it as a transmission line? Okay, so this talks about the FR4, which is what printed circuit boards are usually made of, and that has a dielectric constant that's 4.35 times higher than the dielectric constant of in a vacuum, basically. And then, the assumption is the rise and fall times are a quarter of the cycle time, which basically means that something like this. So you get 25% time for rise, 25% for fall. You stay high or low at 25%. And then comes the next guy. So that's just an assumption for square waves people use. So the question is, at what speed do we need to treat it as a transmission line? Okay, so the velocity of propagation of a signal through a medium is sort of square root dependent on the dielectric constant. And so you take the speed of light. So the velocity of transmission in a vacuum is just the speed of light, 300,000 meters per second. Yeah. And then you divide it by the square root of the dielectric constant. So basically in your FR4, in your printed circuit board, you're at, travel 14 centimeters per nanosecond. So it's a little bit slower than in, nanosecond per foot. Is that right? Is it faster? I guess it's a little bit faster. That's interesting. No, actually 14 centimeters. A foot, 1 foot is 12 inches, and each inch is 2.54 centimeters. So that is 20, whatever it is. That's a big number. So 20, so it's more like 30 centimeters, something like that. So it's about half the speed of light in a vacuum, something like that, which kind of makes sense because we're dividing it down. Okay. So then if you look at the amount of time it takes to go 10 centimeters, you divide that velocity by 10 centimeter, and you go 0.7 nanoseconds in 10 centimeters. So basically you got to make sure that the overall period, like we've drawn here, is each one of these things ends up being slower than, each one of these transitions happens to be slower than this length of time. So overall you come up with, because it's 0.7 nanosecond for the rise, 0.7 nanosecond for the fall, etc., it's 4 times 0.7 nanoseconds is the maximum period of signal that you can think of as not having a transmission line model. And that's your 2.8 nanoseconds. So 350 megahertz. So, there's still a lot of signals that are lower speed than 350 megahertz. So you don't have to treat everything as a transmission line just because they go outside the circuit, outside the chip. But it's sort of that combination. If you're going at 56 gigabit per second, well, like maybe everything, like even if you have a chip that's an inch away or something on your printed circuit board, you could still think of that as a transmission line. But if you're going, gigabit per second, you might have, might not need to worry till you're, quite a few inches away. So it just depends. Okay, so I'm not going to go too much into, these equations for, or at all really into how you derive these equations. But here are two popular, so let me sort of take a step back. So when you're dealing with a transmission line, what you need to do is that the line has something called a characteristic impedance. So this line is made out of lots of little segments of resistance, inductance, and capacitance. Resistance, inductance, capacitance that are infinitesimally sort of represent an infinitesimally small length in this transmission line. So what it's represented as is a single impedance number called Z naught. So which looks like an impedance because it's a ratio of voltage to current of a signal. So it basically represents, you get a characteristic impedance of this line, which is the Z naught. And when you're talking about a 50 ohm transmission line, so this is the 50 ohm or 75 ohm or whatever, those are sort of typical numbers for transmission lines. And if you're going to have something, and we'll see why you need to have a very specific characteristic impedance in a couple of slides, you need to design this in a very specific way to get to a particular characteristic impedance. And again, like 50 ohm, 100 ohm, those are popular. And the structures, the transmission line structures you have in place, the two popular ones on printed circuit boards are the microstrip line and the strip line. And the microstrip line, you don't want anything on any metal layers on top here, so that's why you want to use the outer layer of printed circuit board. And when you are in the inner circuit boards, you have metals on top and bottom, and you can basically use a different transmission line equation. And so, basically you can, on printed circuit boards, you can somewhat specify the height or the width between the different layers. You got some level of flexibility, not a huge amount. So you can, sort of define H. You can definitely define the width of the line, you're drawing that. And then you have, again, some level, maybe not a whole lot of control over the thickness of your metal line, which is all these things that go into a characteristic impedance. Now, one note is that this is, less, it uses fewer sort of precious layers, routing layers on a printed circuit board, but it's like sort of less controllable, let's say, in terms of its impedance than this guy. So at least in my experience, if you want to go very, very fast, so use this one. So because you need that impedance to be very controlled. So this is, the best control you get from having a strip line. Okay, so here's another example, basically just saying, what do you have to do to achieve 50 ohm characteristic impedance? You basically plug all these things. When you make a printed circuit board, you talk to the place that makes it in terms of these ounce copper, which tells you how thick it is, and this material, how thick the dielectric is, and so on. And then you plug this into your microstrip equation, and you solve for it, and you solve for W, and this is ends up with 15 mils. By the way, I think I mentioned this in the package lecture, but this is mils. It's not microns. It's not millimeters. A mil is 1,000th of an inch, or 25.4 micrometers. I'm completely lost as why, inside the chip, in the chip, everything is in units of microns, meters. It's metric units. You never talk about mils inside a chip. When you get to the pad, you start pad pitch, pad spacing, about mils, because the package, people are talking about mils in the package. And then everywhere else in the printed circuit board, all that stuff, everything is in terms of mils. So again, for a long time, I've always thought, this is mils. It's like it's millimeters misspelled or something like that. It is not. It's 1,000th of an inch, okay, or 25.4 microns. No idea. Only in the U.S., I guess. Anyway, okay. So this is why getting a particular impedance is important, is because when you have a transmission line and it gets to the end of the transmission line, depending on this characteristic impedance and depending on the load impedance, you might get part of that signal get reflected back. Okay, so just like you have a beam of light is traveling through air, it hits a pane of glass. The glass is, they call it something else, but it's really the same thing. Effectively, the glass's characteristic impedance is different than air's characteristic impedance, so part of that light gets reflected back to you. And so that's not good if you're trying to get data through here. You don't want reflections. As we'll see, the reflections really slow you down, cause noise, and all sorts of issues. So, and this is the equation for what happens when you hit two different interfaces meet each other with an E and M wave. The amount of the reflected amount is the load impedance minus the characteristic impedance of the line over the sum of the two. Okay, and really you could have, if they're both 50 ohms or if they're both, have, any value of characteristic impedance, it doesn't matter, except it's really hard to get really high or really low characteristic impedance on a printed circuit board or on a cable. So they have, what you'll see a lot is 50 ohm, 100 ohm, and characteristic impedances. You will not, it's rare to see 25 ohm. I don't think it's like hard actually to get to that point, and it's hard to get to 150, 200 ohms because of the sizing and so on. And anyway, so once you're, and then the other nice thing is if everybody agrees, that you're going to make everything 50 ohm. The guy who makes this chip that's got this load impedance in it knows to make that 50 ohm because the user is going to be driving it with a 50 ohm transmission line. Okay, anyway, but that's what happens when you get, and notice if the characteristic impedance of the load and the transmission line are the same, this reflection goes to 0 because of this numerator here. Okay, so let's see what happens. So this is kind of the bad thing that happens if you do not have your impedances matched. So let's say you have a driver that has, it's a very strong driver, so very beefy, these guys. So it's, that's going to output impedance of 10 ohms. Okay, it's driving a transmission line with a 50 ohm characteristic impedance, and it's going to an unterminated line, which would be, an unterminated line would be another inverter, like a capacitor. Okay, so let's see what happens. And we want to plot the voltage at 1/3 point, so here and here. Okay, so and then this is just sort of a matter. This is like time, and these are the voltages. Okay, so plot the voltage at the 1/3 point and the end of the line. Okay, so what happens is, the first thing that happens is you get there's no transmission because this is right butted up against this as you're launching into a transmission line. You just get a resistive divider effect between this guy being 50 ohm, this guy being 10 ohm. So it kind of looks like this. Whoops. Yeah. 50 ohm, 10 ohm. Okay. So basically you end up with an initial wave that looks like it launches at 5/6 of the value. This is assuming your input is a volt. Okay, so 5/6 of that volt gets launched in your transmission line. Okay, so that travels. So this is maybe, I guess this is the 1/3 point, and this is the end of the line here. Okay, so at the 1/3 point, this thing is just launched, so it gets there a certain amount of time, whatever is this time of flight is to the 1/3 point. Okay, and then a certain amount later, it gets to this open transmission line, and because there you have a very high input impedance or infinite input impedance at the load, the reflection is infinity minus 50 over infinity plus 50, and you get infinity over infinity, and that turns into 1. Anyway, this is sort of like there's many different types of infinities, as I've found out in math. These are the type of infinities that in the numerator and denominator they go to 1. Anyway, so 1 is bad news as far as reflection coefficient. It means that you reflect, your reflected wave is the same amplitude as your transmitted wave. So at the output, your output goes, at this point at the output, your signal levels goes to 5/6 times 2, which is 5/3. Okay, so it actually goes above what you launched. And it's now you've launched it back towards your receiver. Okay, so it sort of sits there. At a certain time later, that wave arrives at your 1/3 point, makes that 5/3. Okay, and then you get to here a certain amount of time later, and now you've got 10 ohms sitting there. So now looking this way into this transmission line, looks like you got a 50 ohm and a 10 ohm as your load. So basically This is the reflection coefficient. So you actually go down by 2/3 from what you were. And then you relaunch that back into, so right now we've gone once, we've, gone back, and now we're relaunching this point back. Okay. And so on and so forth. You'll just keep going back and forth, back and forth. And if you look at just your output line, it'll do, this kind of thing, which looks really familiar if you look at a high-speed input on an unterminated line. If you just put your probe here, that's pretty typical. You won't see this. You'll see some nice ringing thing like that. And that's indeed these waves going back and forth, back and forth, back and forth, and creating this ringing structure. So now the problem is, until this whole darn thing is settled, you can't launch your next bit into this thing. So you just have to sit there and wait for this ringing to go away. Okay, and then before you launch your next input. So that's why, anyway, you have to wait for this thing to settle down. Otherwise, the next bit that you shove into this thing will get affected by these waves still going back and forth. They'll start messing with the energy of the next bit. And that's called intersymbol interference. Okay, the symbols are the bits from period to period, and you get that interference between them. Okay, so the minimum bit time, if you're unterminated, turns to several round trips, and it turns into a long period. So you really want to terminate. Okay, so here's the difference between there's a couple of different types of termination. Excuse me, you can terminate at the load, so it means that you put a 50 ohm load here. Your characteristic impedance is 50 ohms. You don't necessarily need to terminate here, because what happens is you launch into this transmission line. You still only get 5/6 of your signal because of the resistive divider between 10 ohms and 50 ohms. And that travels through and gets to this end. But because at that end, you are properly terminated with a 50 ohm transmission line, your reflection is 0. Means you get there and that's it. There's no energy reflected back through your transmission line to cause problems at your source. So it's okay to just have a load termination, and you don't need a source termination in that case. So you don't get any ringing. But you end up with all your power dissipation in the load resistor. Okay, now that power dissipation can be reasonably high, because remember, your power is, for a voltage? So it's V squared over R. Okay, so the lower the resistance is, now we're talking about 50 ohms, which is a pretty low resistance, and the higher this power consumption. So that's pretty high power consumption. I think it ends up being, if it's a volt, this is 50 ohm, I don't know. Is this maybe, anyway, you guys got to calculate it. 2 volts squared over 50 ohms. 102, is it 20 milliwatts? Something like that, which is quite a bit. All right, so the other way you can do the termination is you do the termination at the source. Okay, so let's say you have your 10 ohm source, you add a 40 ohm resistor there, termination resistor at the source, and you get your transmission line, and then let's say this is unterminated. Okay, here, because you're 50 ohm in and 50 ohm transmission line, you start with half of your signal level getting launched. That gets to the end point, and again we have, we're unterminated at the end, so it doubles in value and launches back. Okay, but now when it goes back, when it hits your source, Now your property terminated, so the source basically stops the termination. So anyway, this is also like a reasonable thing to do because at your output level, at your output node, you still see a valid signal level. Things in intermediate points in the transmission line see this sort of funky multi-step thing, but at the load you don't really see any issues. And here the power gets dissipated in the load, that V squared over R. Again, depends on your voltage swing. Okay, so it's just a summary of issues about termination. Now, one of the things about termination is that it's really for a point-to-point link, like something like this. A talks to B, B talks to C, A talks to C, but not for a multi-drop bus. Because those are, remember when we talked about, if you're talking about source termination, it's sort of hard to do termination. I guess it says you can do load termination, but you have all these stubs. Anyway, it's bad news. I would not try to do sort of a high-speed multi-drop bus, or you won't be able to go terribly fast, and you got to model it very carefully. Okay. The other aspects of noise that you could get in a transmission line is you have this effect called dispersion. And dispersion means that when you have a transmission line, not all the different. So when you have a square wave in a signal, these rising and falling edges have all sorts of frequency components. It's not just one frequency. It's like doing a Fourier transform of this guy in the frequency domain. So what you'll see is a lot of harmonics. And each one of those harmonics, those frequencies, travels through the transmission line at a different speed. Okay? So what happens is you launch a square wave, but because these things, the different energies of the different parts of the frequency of that square wave travel a different distance, you'll end up getting a broadening and a lowering of the height of that bit. And so at the receiver, you'll see this dispersion. And if you launch bit after bit, this guy hasn't quite settled by the time the next guy comes along, and so you get this thing called, again, intersymbol interference. And then you have crosstalk issues, having both with capacitive and resistive crosstalk. Okay, so let's see. So what I have to say, I guess this is sort of just summarizing the stuff we've been talking about. And then, talking about all these different things, there's a bunch of options on how do you design a transmission line. These are design choices, and they're all valid. And so you get a variety. You get either single-ended or differential signals. Single-ended or differential. Sort of common ones for differential are current mode logic or LVDS, and I don't know if you've seen either one of these, but in terms of speed, this tends to be the highest speed interface, this current mode logic. And one version of the current mode logic is drawn here with open drains, but there are different options. And LVDS is actually a standard, this low voltage differential signaling, so there's well-defined common mode levels and differential swing levels, etc. for this thing. This goes fast, but I think maybe you can do 1 to 2 gigabit per second with this guy. This guy can go really fast. This is like stuff that goes at 56 gigabit, tens of gigabits per second. Okay. And then you could do, what's called push only, where you have you got an open drain like you have here. So you're just pulling current this way or this way, and you're terminated at the output. So your load is sitting at your output, and you're pulling current in. And this guy's pulling, this guy's creating your 1 and your 0s when you're pulling down. Same with here. Notice that you've got an NMOS here and an NMOS here to push and pull. Basically, the reason you've got an NMOS here is because PMOS FETs are slow, and you want to have sort of high-speed lines. So you've gotten rid of the PMOS, but you're not going to go to the full supply voltage, but you got rid of your PMOS, so you can drive it. Plus, it's easier to get a characteristic impedance out of a source follower, a low impedance, than it is out of a PMOS, which is going to have a high output impedance. But anyway, we're not going to get to those. Just leave it that there's a few different options that you have for transmission lines. And I really do see all these different ones all the time. Certainly CML, LVDS. You see stuff like this. It's more like sort of DDR memory interfaces, etc. So you see all these different options on. There's really not a standard, I would say, that all transmission lines are going to work. All the transmission line drivers and receivers are going to work the same way. But so you better make sure the receiver you're choosing is appropriate for the driver you've got, and same things with the termination, that it's appropriate for the transmission line that you're using and the driver that's driving you. Okay, another question on the receiver side is, how do you sort of sample where? So this is a typical eye diagram. Honestly, it's a pretty nice looking eye diagram. And what an eye diagram is you put your oscilloscope. I don't know if this is going to make sense to you guys, but you'd have to do it to see it. So what you do is you trigger the scope off of your input data, okay? And since your input data is random, so you're not triggering off the clock of the data, you're actually triggering off the data itself. And because it's random and you put your scope in persistence mode, that means it's putting these waveforms on top of each other. You basically get an averaging of all the type of bit conditions on top of each other. Of all types of, zeros followed by 2 ones, 0 followed by 3 ones, 0, 1, 0. 1 followed by 0. All those things sit on top of each other, and because they all have some level of intersymbol interference, you get these funky effects like this, or this might just be a reflection, or it could be intersymbol interference. Anyway, be that as it may, this is called an eye diagram. And the reason it's called an eye diagram is because supposedly this looks like an eye, and the more open that eye is, the easier it is to grab the sample. And the best sampling point is indeed this point, because you've got you're far away as possible from these two edges, and you've got a nice 1 and a nice 0 here. Okay, but how do we know when that is? So we need a clock. So we got 2 strategies. One of them is called source synchronous clocking, which means that you've got a bunch of channels that are sending data, and you try to match basically all these channels, and so these would be the data channels. And then you send on one of the channels, you actually send the clock, and you can use that clock to grab these data. Okay, so this works up to a certain speed, but after a certain speed, this doesn't work anymore. Okay. Oh, and then another thing you can have is single versus double data rate, and all that means is single data rate. So if you have a clock, usually only on the rising edge of the clock do you get valid data, but you can use both rising and falling edge of the data. So that's why it's called a double data rate. And memories work that way. Those are the DDR, I don't know, T3, DDR4 memory standards. So anyway, you can sample on both edges of the clock, get a little bit higher speed. And if you're using this DDR interface, you'd like to get, your data got launched on some edge, but you want to now sample at, a quarter of a period later. And if you guys remember the delay lock loop or the phase lock loop, what we can do is, we've got an oscillator going that's oscillating at the same phase and the same frequency as the clock. But if you tap off exactly the middle of your oscillator, basically you get to a 90-degree point from your clock phase. That doesn't matter what your clock frequency is. This point will always end up being at the 90-degree point, just because it's always dividing your clock by a factor of 4. Okay. Notice when we talked about the PLL, I was saying a voltage controlled oscillator, you always need an odd number of stages to get an oscillation. But this is a symbolic representation, so they've inverted. You've got an even number of stages, but one thing got inverted. So basically, you still can get oscillation with an even number of stages. It gets much more tricky to design. Okay, so that was one thing, a source synchronous clock. The other thing to do is to actually, that only works up to a certain speed, because after a while it gets really hard to match your lines exactly. So what people do is they actually use the data itself to extract the clock from. And so the idea is you use the data and the clock as part of your phase lock loop to basically sort of recalibrate the edges of the clock. And sometimes you actually don't even bring in a clock. You just use the data itself to extract the clock and grab itself. So anyway, lots of different options, but at higher speeds, you're going to see really sort of some very complicated ways to detect the data clock and extract it. Anyhow, that was it for the I/O. Again, like another field that's very complex, very rich. There's still a lot of exciting stuff's going on. And anywho, that's the end of our technical classes. The next one, I think, will be a review of everything we've done from the midterm onward. Take care.